Hello and welcome to this tutorial for nuclear reactor design. In this tutorial we are going to be covering some basic nuclear physics example questions. The first question is, what is the energy equivalent to one unified atomic mass unit, or AMU? To solve this problem, we are going to be using the mass-energy equivalence equation, E equals mc squared. Next, we will convert the one atomic mass unit into kilograms. Then take note that c is the speed of light, which is equal to 3 times 10 to the power of 8 meters per second. After plugging in the numbers to the formula, we see that 1 AMU is equal to around 1.49 times 10 to the negative 10 joules. The next question we will be looking at is, what are the products of these radioactive reactions taking place in each of the following situations? And by what mode are they decaying? The first reaction is uranium-238 decaying into something and a helium particle. In the second reaction, we see cesium-137 decaying into something, an electron, and an electron antineutrino. The last reaction is tritium, which undergoes the same decay as the example above. To solve this question, you will want to look at a decay chain for the elements we are looking at and see which nuclides are produced with each mode of decay. In this reaction, we had uranium-238 decay into thorium-234 by mode of alpha decay. We know this because of the helium-4 particle that is produced when the uranium decays. The second reaction had cesium-137 decay into a metastable isotope of barium-137 by mode of beta decay. We can tell it is beta decay because an electron and an electron antineutrino are produced during the reaction. And in the last reaction, we had tritium decaying into an isotope of helium-3 by mode of beta decay as well. The last example we will be looking at is, we have a sample of radium-226. The half-life of radium-226 is 1,602 years. Radium-226 has a molar mass of 226 grams per mole. If we have 1 gram of radium-226, what is the initial activity in the units of Curie and becquerels? Next, we will want to find the activity after the sample has been through 1 half-life and after 5 half-lives. First, we want to find the activity, which is found by multiplying the decay constant by the number of nuclei. The decay constant is equal to the ln of 2 divided by the half-life. Here we calculate the decay constant, but you will notice that we are converting the half-life from years into seconds. The decay constant is equal to 1.372 times 10 to the power of negative 11. Now we need to find how many nuclei we have, and to do this we are going to divide the mass of the sample by the molar mass and multiply that number by Avogadro's number. And the answer to this is 2.6646 times 10 to the 21 nuclei are present. Now we can solve for activity with the numbers we have. The activity of the 1 gram sample is equal to around 3.66 times 10 to the power 10 becquerels. 1 becquerel is equal to 1 decay per second. Next, we are going to convert to curies. 1 curie is equal to 3.7 times 10 to the 10 becquerels. After converting, we see that the activity is equal to 0.988 curies. Finally, we are going to calculate the activity after 1 half-life and after 5 half-lives. These values can be easily calculated by dividing the initial activity by 2 for every half-life that passes. We would need to divide the initial activity by 2 5 times to get the activity after 5 half-lives. The activity after 1 half-life is 1.83 times 10 to the 10 becquerels, and after 5 half-lives, it's 1.144 times 10 to the power 9 becquerels. This will conclude the tutorial.